Hello, welcome to my presentation. My name is Pankanti. I recently graduated from Purdue University with my bachelor's degrees in computer science and agricultural engineering. My presentation's topic is fine-grained recognition in high-throughput phenotyping. In other words, how to classify subcategory plant cultivars. The co-authors are Mr. Smith and Dr. Chikar. I would also like to acknowledge Dr. Rennie, Purdue Computer Science Department, and the funding from USDA. First, what is high-throughput phenotyping? It quantifies phenotypic traits of individual plant cultivars by using high-throughput image collection and analysis. Like in the figure below, researchers can plant crop plots in the field, outdoor, or individual plant cultivars indoor. We can also use different imaging devices, like the mobile ground platforms, drones, and even aircrafts. Unlike traditional plant imaging, HTP has several unique applications. Genetic selection, or plant breeding in agronomy, because now we are studying the unit of plant cultivars. Water stress evaluation, because we are studying the phenotypic traits of the plant itself, like vegetation indices with additional information like soil moisture and irrigation practice. Also, yield prediction at a very high resolution of plant cultivars and also at a high throughput. For example, in our experiments per year, we collect millions of images for thousands of plant cultivars. Now, what is fine-grained recognition, FGR? It's an emerging topic in computer vision, and its goal is to classify subcategory objects like car models, which is very different from traditional classification like just cars. And in the context of HTP, the goal is to classify plant cultivars, and this may directly help plant image extraction and phenotypic trait discovery. But there are also challenges, like easy overfitting for complex features and models, because each class are just very similar. We can also face changing visual conditions, like in the right figure of the soybean plot images collected by drones. Inside each class, each examples may be different from each other by view angles or growth stages. And also high throughput, because like in our experiment per flight, we collect thousands of images, so the method has to be efficient. To solve these challenges, we start from a very simple, intuitive, and robust feature descriptor. We call it a radio object descriptor, ROD. Here's the feature extraction pipeline of ROD on a soybean experiment site. First, we use drones to click the images of the soybean experiment site, and then we extract the soybean plot images by using signal processing and ground calibration techniques. We further segment out the main canopy by removing the noises. Then we do contour tracing to get the two-dimensional contour. And then we unfold this two-dimensional contour into one-dimensional XROD vector. This process is very intuitive. That is, XROD is the relative Euclidean distance between each contour point and their closest counterpart on the center line, the gray one. As a result, ROD is invariant under scaling, rotation, and translation. You can see the proof in our paper. It's also robust under the change of growth stages because it's similar to uniform scaling. It's even robust under change of view angles because it's like partial stretches of the 1D vector. And this pattern may be learned by the regression model. Based on previous studies, we are also aware that feature fusion may potentially improve the ROD in classification models. People have successfully fused low-level, mid-level, and deep features to solve similar problems like medical image classification and face recognition. In our case, we similarly concatenate ROD with histogram of oriented gradients and resident 18 features in the softmax regression model, respectively. Here's a sample figure to show the effectiveness of fusing ROD and HOG to classify two soybean classes with images and different view angles. If you look at the HOG features, you can see that most of its discriminate features are along the contours, or the top and bottom parts with red and blue colors in the filter heat map. If we look at the ROD features within the same class of different view angles, we can see that they still correlate with each other very well. Between each other, we can see that their RODs differentiate against each other very well. This is also reflected from the filter heat map of the ROD. You can see that although it's very simple as compared with HOG, most of its part is very discriminative with red and blue colors. The feature fusion strategy mentioned in the previous slide is summarized into two approaches: ROD Hog softmax and ROD resonate softmax, as in the left table. They are compared against 5 traditional approaches, and they are tested in 4 datasets. The first dataset, HDB soil, is a local benchmark dataset we collected from outdoor soybean plots, totaling about 1,700 images. The rest of 3 images are collected from indoor roseate plant images from previous studies, totaling about 2,500 images. Here are some sample images from the 4 datasets. These images can explain why we see that there are so many challenges for fine-grained recognition in HDB. If you look at the HDB soil dataset, the 2 different classes of soybean plots, they're kind of hard to distinguish if you use complex features or models, which may cause overfit. They may also have different view conditions. If you look at soybean plots, their shadow will appear on different sides for different replicates, which may indicate different view angles. They also have different growth stages. Once the canopy will keep growing and their appearance will differentiate. Similarly, for the rest of 3 indoor roseate plants, although they don't have view angle changes, their growth stage changes are still very significant. Especially if you look at the bean, it's very sensitive to the nighting conditions, so during the night, its canopy will even close. Okay, here are the classification results. Basically, ROD resonate softmax achieves the best mean accuracy for classification. And I think there are 3 takeaways. First, it's reasonable to say that because deep features come from the state-of-art feature extractor, Resonate 18. Second, it's surprising to see how ROD softmax can achieve very good classification results similar to Hog softmax and has a little margin as compared with the others. It's even more surprising to see how ROD could improve Resonate to jump from 80% plus to 90% plus, like for the HDB soil. Third, ROD softmax still has limitations. Like for the Arabidopsis, ROD softmax just reached about 50%, which is still far better than the full-year softmax, but has a large margin as compared with others. Here's another experiment where we train and test the classification model in different growth stages. Results can also be summarized into 3 takeaways. First, low-level and mid-level features tend to generalize better than deep features as you compare the 2 rows. Second, it makes sense to see that growth stages with longer day intervals tend to generalize worse because canopy just change more significantly. Third, it's very interesting to see that later growth stages, as seen on the top right corners, tend to generalize better. These type of results may help us discover phenotypic traits in the future. Thank you for watching this. Please email me if you have any questions, and here are the references.